So just now we introduced how to calculate the entropy change for a process. Like we can use the heat of the system obtained or loosed, divided by temperature, the temperature. Like for example, if it's weight, we can use in the enthalpy to change the entropy. Okay, now the question. So, calculate the standard entropy of vaporization of acetone nitride at the acetone at its boiling point of 329.4 Kelvin. We know the standard heat of vaporization at its boiling point is 29.1 kJ per mole. So how to calculate the entropy change for this during this process when the acetone changed from liquid to changed from ice to liquid boiling point, okay? And we know during this process the enthalpy change is this angle, and the boiling point is this temperature. The enthalpy change, like the heat, okay, is this angle, and the boiling point is this one. Monitor.
The entropy for vaporization. So you take the standard heat.
Yeah.
Since the general formula is heat over the
temperature, yes.
So you take the standard heat vaporization.
So what's the heat during this process? Lava? What's the heat? What's the heat?
29.
Which one? What's the heat? This one, right?
Yeah.
Okay, and temperature is this one, right?
Yeah.
Good. So just using this number divided by this number. Yeah, it's easy. Okay? And the unit, you have the unit of the entropy is joule per Kelvin per mole. Okay. So this table to show some standard entropys. So standard means the heat. This is what we use. Is one atom. Just means one atom. Okay. The temperature is boiling point. And we can say here the enthalpy change. So during vaporization for substance, we can get this number, and also this number you can find from books. Okay. Okay. So now we introduce what is standard molar entropy of substance. Now it's not an entropy change. We just talked about the entropy change of the process. Now we understand molar entropy of substance. Just means for each substance. So the standard molar entropy we like S. Okay, 0. So standard molar entropy. So standard means here is the pressure is 1 atom. Okay, and the temperature is 25 degrees. 25 degrees is also like 298 Kelvin, right? So in this state, so all substances have their own standard molar entropys. And the unit is this. From here we can see the entropies of all substances. Okay, they are standard molar entropies. Okay, so we can use these values to calculate the entropy changes of reactions of reactions. So this is called like stand reaction entities. So stand reaction entities equal to the using the products entropy minus the reactants entropy. Okay? So this is the reaction entropies. For example, for this reaction, okay, and its standard reaction entropy is equal to the products entropy minus the reactants entropies. And for this, we can get this substance entropy from books, okay? And then finally we can get the numbers like this. So from here we can say the standard reaction entropy is lactive for this reaction. Lactive reaction. As why we say this is expected. Why? Why do you think before the calculation from left to right the entropy should be decreased? Why? And of course, after calculation, the number is lactive. From the reaction, we can also say from left to right, definitely it will be lactive. This means the entropy change will be lactive, or the entropy of the system will decrease. Why it will decrease? Yeah, not any. No or not? Why? From the reaction. Yes, the amount of left is more than this one. Okay, you can see from say here is 4 more, right? But here only 2 more, and this side has more molecules, right? And of course, more molecules they have more freedoms, right? And so from left to right, definitely its entropy will decrease because it becomes have more fewer molecules. Okay. So any question for this? Okay. Entropy means freedom, arrangements. Okay. Yeah. Disorders. Yeah.
Yeah. So if you're comparing, let's say, nitrogen gas and this gas is said, so we're going to say this gas is said, yeah, it's going to have more entropy than nitrogen gas, right?
You mean this one? This one?
Yeah.
This one have more. Yeah.
Comparing the two.
Yeah, of course. Just if only compare these two.
Yeah.
Of course, this guy has total. Okay. But for whole system, the whole system, of course, this has more disorder than this guy. If only these two, this guy has larger disorder than this guy. This guy also has larger disorder than this guy. But total, okay. And also you can consider the number of molecules. And of course, if the system has more molecules, of course it will show more disordered, right? For example, do you remember we have if both sides only 2 molecules, right? There are only like 4 arrangements, right? But if I have 4 molecules, it has 16 arrangements, right? So of course, if the system has more molecules, it has more disordered, and its entropy increase. Okay. So yeah, reactions that increase the number of gas phases molecules tend to be accompanied by positive changes in entropy. Positive change, of course, but this is a decrease, right? From the decrease. If we increase, the entropy will increase. Dissolution reactions are typically accompanied by an increase in entropy. Why? Okay. Yeah. Why dissolve for substance? If the substance dissolved in solution is dissolved, and the entropy will increase.
Actually, because when dissolving a solution,
Yeah.
So maybe the increased number of
No, their number. Their number no change.
I mean like the space.
For example, sodium chloride dissolved in water.
Yeah.
Okay. Numbers of atoms doesn't change.
Even changing state.
What?
Because I mean like when you sodium,
Yeah.
when you put it in water,
Yeah.
I mean like it will dissolve in water.
Yes.
So
It's like from solid to
Yeah.
liquid, right?
yeah.
And of course, we know in liquid has more disorder than solid.
Yeah.
Yeah. So this is why if the solid is dissolved in solution, so this process its entropy will increase. Okay. But however, of course, there are examples where the opposite is true. This, for example, from left to right, the entropy decrease. So why sometimes the entropy will decrease? The solid and liquid will usually it increase, right? But why in this case decrease? Whose turn? Whose turn?
It's my mind.
No, you are more close to the back. Your turn. Say, you can say this that. Okay. Yes, say no. Yeah, you can also try. Okay. Hope you. You know what? So who knows this answer? Who knows this question? Who knows why in this case? We know basically, say from left to right, and it looks like there are more. The atoms are more free, right?
Yeah.
But from left to right, it is with entropy. This for this process, right? The reason is because when it is dissolved in water and it will surrounded by water molecules, right? So after it's surrounded by molecules, so for now the system is not only this substance. The system should also include the water. Okay? So when it is only at first water can move everywhere, right? But when they come into water, so the water have to surround them, right? Form some interaction, right? So the freedom of water increase or decrease? Yes, decrease. So for whole system, there are freedom decrease. The freedom of this substance, metal and chloride, their freedom increase, right? But the freedom of water decrease because the water have to surround them, so they can't move freely. So for whole system, the freedom of water decrease. The freedom of this substance increase, but the total freedom decrease. So this process, after this process, is entropy change is decrease.
So
Yeah.
for the total entropy, you pick why did we have to pick for what?
what?
The total entropy of the
Yeah, the total entropy should be equal to the entropy change of the substance, metal, and add the entropy change of water.
so we pick for water because for those ones they are reducing the entropy because but
Yeah.
for the water.
No, the entropy increase.
Oh yeah, the entropy
Yes,
increases, but
yes,
for water
yes.
it reduces.
But those, yes, but those, yeah.
So
But
we have
the sum number, sum of the entropy decrease. Because the freedom of water decrease, and decrease much more than the increase of these two guys. Yeah, so the whole system freedom decrease. The whole system means the metal, this two ions and the water. Okay, sure.
we consider the water.
Yeah, the number, the value of change is different. Are different. For example, this process, this is maybe just the entropy change is just -1, okay? But for the water, its entropy increase is +2. Okay. So in this is the increase, right? If we increase like this is +1.
Plus one.
But the disorder of the water decrease is -2. Okay, so the whole change is still negative. Okay, yeah.
So in terms of those numbers, like you said, -2 and 1. So do you have to subtract or you just get -2 for the whole thing? If you, in terms of numbers, you say
Yeah,
the
water.
the water entropy will be, since it reduces -2. Give an example as -2.
yes,
Then for those ones, the
Just
increase
+1.
is +1,
yes, but total
but total
is -1.
-1.
Yes, yeah, -2 add 1, right? -2 plus 1, so the total is -1. -1 means is entropy decrease, right? Okay.
Ah, for example.
What has it to do?
What's wrong?
Where the system
Where's the
Register in participation.
Okay. So now we know the entropy, how to think about the entropy change of the system. Now we introduce the second law of thermodynamics. So we know, so basically, for this process are spontaneous. Well, it is true that most spontaneous processes occur with an increase in entropy of the system. There are examples of spontaneous processes that appear to occur with decreased entropy. For example, from left to right, its entropy increase or decrease. From ice to water, increase. Okay. From water to ice, decrease. So, but we still say when the temperature is lower than 0 degree, from water to ice is also spontaneous. So this means for this spontaneous, its entropy decrease, right? Decrease. Okay. So for example, below 0 degree water spontaneously freezes, even though the process is accompanied by a decrease in entropy. When water freezes, the heat liberated is taken up by the surrounding, whose entropy increase. So this is, water change to ice. For water, its entropy decrease, right? But for surrounding, because it get heat from the surrounding, right? So this means the surrounding, the temperature of the surrounding will decrease or increase. The surrounding like you just put it the air around the glass. The temperature of the air around the glass will decrease or increase. Decrease, yes. So the air temperature decrease. So the air's entropy increase or decrease? Decrease, right? Because temperature become low, so it entropy decrease. So this is why this process can be still spontaneous. The reason is, even though the ice, the water ice entropy decrease, but the entropy change of the surrounding decrease. Okay, decrease. So here we can say change in enthalpy of the universe. So universe, you can say the universe, we can say equal to the system. The system is water, like water ice, and the surrounding. So here surrounding is like the air around the glass. Okay. So we can say the whole universe and there will be change equal to the system equal change and the surrounding equal change. So when water changes to ice, so this number is negative or positive. This number for the system is actually decrease or increase. Water change to ice. Yeah, decrease. So this number is negative, right? Negative. So water changes to ice, so this number is negative. But when water changes to ice, it will release heat, right?
Yeah.
Release heat, so the surrounding get heat, right? So the surrounding get heat, this means the surrounding, this number will be positive. Positive, okay. And finally, this number and this number is a change of universe. Of the universe. So now we can say the second law of thermodynamics is like this. For a process to be spontaneous, the entropy of the universe must increase. If this process is a process, if one process is spontaneous, the universe entropy must more than 0. Okay, so this is the second law of thermodynamics. So the entropy of an isolated system increases in any spontaneous process Y. Now the entropy of an isolated system. Do you remember isolated system? We introduced a system, right? There are 3 systems. Open, close, isolated, right? So isolated system, what's an isolated system? Do you remember? Okay. What's isolated system? The heat can be changed or not?
Not.
No. The substance? No, right? Okay. So in an isolated system, the entropy must increase. Why? What's that? Okay, got it. So from here, we can say from here. So the universe should be increase, right? Now, even with the in system and surrounding, in an isolated system, no heat exchange between the system and the surrounding, right? So this means the change, the enthalpy change of surrounding will be water.
As
What this number? What this number should be? Surrounding.
Can you ask again? I didn't get your question.
The question, like for example,
Uh,
for a spontaneous system process, this number should be more than 0, right? Now, in an isolated system means no heat exchange between the system and surrounding. So this means the surrounding. We know delta S equal Q divided by temperature, right? Now Q is 0. So what the number should be?
0.
Yes. Okay, so the surrounding, enthalpy change of surrounding is 0. So of course, the system must be more than 0. So this is here. The entropy of an isolated system increase in any spontaneous process. Increase means must be more than 0, okay? So in an isolated system, because this is 0, so systems should be positive, must be positive, or in a spontaneous. Okay? Now this is about the second law. Second law is means for a spontaneous process, the enthalpy change of universe should be increased. Should be increased. And of course, universe is equal to the system and its surrounding. Okay? Okay, now it's like this. Okay, we can use this picture to show for example, this is the system, right? This is the surrounding. This is surrounding, okay? And so the whole is a universe. So in these two cases, we can say the system release heat to surrounding. So the surrounding entropy will increase, right? And if the system, the entropy of the system, of course it releases energy, but it still maybe its entropy increase. For example, after the reaction, the system has more molecules, right? Even though it releases heat, but it has more molecules now, so its entropy also increases, right? So in this case, of course, the total entropy change of universe is this guy and this guy, so it's positive, right? It's positive. So this reaction is spontaneous. Okay, in this case, now the system release energy to surrounding and then of course the surrounding get heat, so it's increased. After the reaction, the system the entropy may decrease, but the volume of decrease is small than that of increase. So the sum entropy change of the universe is still positive. It's still positive. So in this case, this reaction is also spontaneous. Why? Because the total entropy change is positive. It's positive. Because this decrease number is less than the increase number. Okay. So for this, in this case, this reaction is also spontaneous. Okay, in this case, this means the system get heat from the surrounding. Okay, so the surrounding provide heat to system. So the temperature of the surrounding will decrease. So its entropy change is negative, exactly. But the system get heat, and after the reaction, its entropy increase, and the volume of increase is larger than that of decrease. The sum entropy change of the universe is increase. So this reaction is also spontaneous. It's also spontaneous. So this here introduced three cases. In all these three cases, the sum enthalpy change of the universe is positive. So this process is spontaneous. Why is it spontaneous? Because the total entropy change is positive. And this is about the second law. Okay. So here, if the universe, the entropy change is less than 0, it's like a negative. If the change is negative, and of course it's non-spontaneous. If more than is larger than is positive, so it's spontaneous. Whereas it's equal 0. Equal 0, what this means? This means the changes of the universe system and surrounding is the same, but one is negative, one is positive. Okay, where it is 0, so the process is at equilibrium. Okay. So here, no process that produce order in system can proceed spontaneously without producing an equal or greater disorder in its surrounding. So this means if for a spontaneous process, if the system's entropy decrease, so the system's entropy change must be positive. Okay. So unlike energy, entropy is not conserved, and the universe entropy change is always increase. It's always increase. This is also like the explosive theory of the space. Okay, and the universe of the space entropy must be increased. Must be increased. Okay, now we introduce the Gibbs free energy function. You know, to determine the entropy change of the surrounding is usually very hard. For example, after the reaction, the surrounding, the environment, the entropy change is hard to determine the entropy change of the environment, right? So, to determine if a process is spontaneous or not, we need a way to account for the change in entropy that the system undergoes. So a better way, this means a better way is we just only determine the spontaneous only through the change in the system. So we're using the Gibbs energy function G to determine the spontaneous knot. So what is G? So G, we just a constant quantity. At the constant pressure and temperature, the G equal H minus Ts. So you should remember this equation. What is Gibbs free energy? So the Gibbs free energy is equal to enthalpy minus the temperature times the entropy. Okay, this is the Gibbs free energy, and the units of the G is joule. Okay, because you know this the heat, the unit of heat is joule, and time and this this guy will be also joule. So Gibbs energy, free energy is a state function like H and S. Now we know the free energy. We can write the standard Gibbs free energy. So we know the standard enthalpy and the standard entropy. So we can calculate the standard Gibbs free energy. Okay, it's like use this way. So here. So this means at the 25 degree and 1 atom. So this is called the standard Gibbs free energy. So it's come from the standard entropy and the standard enthalpy and the standard entropy. Okay. So and of course we can calculate the change in the free energy function for a system. So here, this because G equal H minus Ts. So delta G equal delta H minus T delta S. But all this is about system. Now we can use this energy change of system to determine the spontaneous or not. Okay, so why? So here to show. So we know this is system, this is surrounding, and the reaction release energy. So the surrounding get heat, and the surrounding temperature increase. So its entropy increase. Okay. In this case, the surrounding provide heat to system. So its entropy decrease. Assume that surroundings are so large that the temperature and the pressure remains constant. What this means? This means in this case and in this case, the surrounding get energy. In this case, surrounding provide energy, but the temperature they almost remain constant, because you know the universe is very large. So the temperature, for example, in this case, the temperature may be very small, right? And also in this case, very small. So we can say, and the change of system is this guy. So the surrounding, we know the surrounding for the surrounding, the heat is this level, but the temperature change is like zero. Like zero, so this means it's always the surrounding, for the surrounding, the temperature will not change.
So it's constant.
Yeah, okay, it's constant. So this is the third law, right? Okay, Herschel.